So it's nice to be here again. Thanks a lot for showing up. I know it's the morning, and I know I have many mornings, so you will start the day often with me. I hope you will enjoy it. So today what we're going to do, we're going to stay still in dimension 1, which is where we started yesterday for our class in holomorphic dynamics. So you remember yesterday I ended giving you a couple of statements, but they were like a skippy, meaning that I didn't define everything. So now we're going to get a little step back and to, well, first define something that I used, and then I noticed I had not defined. So I have told you, oh, you know, whenever you change coordinates, so you start with the dynamical systems. Well, for the moment, let's start easy. So we have our rational map of degree D. Okay? Because this is where the dynamics is going to be interesting. And I said, well, you can always change coordinates, but what do I mean by this? So what do I mean is that if you somehow, so you have your map, and your map is there. You have the Riemann sphere, and that's an object which is intrinsic. And then you choose coordinates to make computations, right? But then, well, who tells you that these coordinates are the best choice? Nobody. So you could have other coordinates where your map is in a better shape, and it's easier to iterate. Okay? And so this is what we usually call a change of coordinates, and there is a definition for this, so I'm going to put it here. So two rational map, so two rational functions, yes, f and g are topologically. So I started with this, but this is not a good choice. So let me go for this one. Or analytically conjugate if there exists a homeomorphism, in this case, or a biholomorphism, so a analytic isomorphism, in the analytically conjugation case, phi from C hat to C hat, such that, well, what you have is that phi composed with f is equal to g composed with phi. Okay, and since we have something which is invertible, because in the topological case we have a homeomorphism, and in the analytical case we have a biholomorphism of the Riemann sphere, well, this is equivalent to saying that phi composed with f composed with phi minus 1 is equal to g. So what does this tell us? It tells us that whenever I iterate, so as a remark, what you have is that, okay. Yeah, I think it's supposed to work out. So what happens is that if you consider G iterated k times, well, this is the same as doing phi composed with f, composed with phi inverse, composed with phi, composed with f, composed with phi inverse, composed with da-da-da, phi composed with f, composed with phi inverse k times. But as you see, since, well, I put this parenthesis just to remind you that this is a G, this is a second G, and this is a kth G. But as you see, well, if I erase this parenthesis and now I take this once, since phi is invertible, this is the identity. Right? And so this is simply equal to phi composed with f iterated k times composed with phi inverse. meaning that not only you have that the two maps are conjugated, but when you iterate in G or iterate in F, it's easy to understand. Okay, and so if you know that for your map, for the G map, it's easier to understand the dynamics. So say it's linear. Of course, it's not going to be linear. Well, say it's z to the power d. Okay, if it is z to the power d, then iterating z to the power d, iterating z squared, it's easy. All right. Whereas iterating the original map, which was not z to the power d, might be difficult. Okay, and that's why analytic conjugation or topological conjugation are important. So we could have, actually, so in here I'm putting just two. So analytical conjugation is going to give us, is going to preserve all the properties. So also the velocity that you have going towards something. So you are having exactly the same image. It's just I changed coordinates and that's all. Whereas if you consider the topological conjugation, it's like you are deforming topologically. So you're not keeping the analytical properties. So if there is an orbit for G converging to a point, there will be an orbit for F converging to a point, which is the image via phi. But you will not know whether or not they're going to go at the same velocity. Okay, that's something that you will lose. But at least you will have an image of what happens to your dynamical system, which is already something. And, yep. So, and I think that in here, yes, okay. And of course, we would like to know whether we can say something about the Julia set and the Fatou set, right? And because that's what it is our interest. By the way, before I go on, let me remind you, so again a remark, that, well, the only analytic isomorphism of C hat are the Möbius transformation. Meaning z goes to az plus b over cz plus d with a d minus bc different from 0. And the analytic isomorphisms of C are the affine maps. So z goes to az plus b with a different from 0. Okay, so these are the only analytic isomorphisms, the global maps. Of course, you could also, and maybe, I don't know if we'll go there, you could also say, okay, maybe I don't want to understand everything for the global maps. Maybe I just want to know what happens in a tiny neighborhood of a point, which is important for the dynamics, like a fixed point. And then you can give exactly the same definition, but locally. And so this will give you an information only nearby the fixed point, which is already something, but not concerning the Julia set or the Fatou set. Okay, you remember that the Julia set is the chaotic set, and it's the complement of the Fatou set, which is the stable set, where you have normality when you have convergence up to subsequences. Okay? All right, so there is a proposition, as I was saying. So if F and G are analytically conjugate by phi, then, well, it happens what you expect. The image of the Fatou set of F is going to be equal to the Fatou set of G. And, of course, the image of the Julia set of F is going to be equal to the Julia set of G. All right, and so as an exercise, you can do the following. So you can consider A different from B, complex numbers, and set P of Z, which is simply going to be Z minus A times Z minus B, if I'm not mistaken, yes. And you can try to show that the Newton methods that you might have encountered when searching the roots of a polynomial. And well, actually, this is again a dynamical system. So this Newton method is going to send Z to, well, Z minus P of Z over P prime of Z. Okay, so this is the Newton method. And what you do with the Newton method, you're doing dynamics. So you start with a point, and then you apply it, and then you take this point, you apply it again and again and again. So you're iterating your map, okay? And if you're lucky, meaning if you started not too far from a root of P, you're going to converge to your root of P. So this Newton method is conjugate to the map f of w equals w squared via, well, the map phi of z, which is going to be equal to w, equals z minus a over z minus b. And then you can determine the Julia set of the Newton method and the omega limit set for, well, each point in the Riemann sphere minus the Julia set of the Newton method. Okay? And a second exercise that you can do, you can show that the two Newton methods and P of z equal to z minus P of z over P prime of z and Q of z equal to z minus Q of z over Q prime of z. So I take two polynomials and I consider the two associated Newton methods are analytically conjugate as soon as you have that Q of z is equal to lambda P of alpha z plus beta for some lambda, alpha, and beta complex. All right. So now that we talked about, conjugacy and how so actually why is this interesting now? Because, well, with this definition, it makes it easier to compute the Julia set or the Fatou set for maps that are conjugate to simpler map. So we studied W squared yesterday, and you studied also z to the power d with d bigger than 2 or d less than minus 2. And, well, for those maps, it was easy to understand the Fatou set, and then therefore the Julia set. For all the maps who are conjugated to these maps, the Julia set and the Fatou set are easy to determine. But most maps are not conjugate to this elementary map. So actually, there are some maps, there are some functions in complex dynamics in dimension 1 which are called elementary. These are the power maps and Chebyshev maps. And that's all. And also Laplace examples, we will not enter to that. And they are called elementary because, for example, they have several properties. In particular, you can compute the Julia set and the Fatou set in an easy way. But most maps are not elementary. Most maps are a mess. And so, well, when you start to study them, it's a good thing to start by searching for easier place. So instead of looking right at the Fatou components, you can first start by looking at periodic points and classify them. And once you have classified them, you can also, so in dimension 1, it's really important to also look at the critical points. I will not enter too much into that because, well, in higher dimension, the critical set gets highly complicated. And also, what do you mean by critical set? And then you could have indeterminacy sets. We are not going to enter into that because, well, I had to make choices in preparing these classes. But a first idea is that let's see how we can, well, classify periodic points. Are periodic points all the same? Well, we've seen in our baby example, let me remind you, it's my favorite example, was z squared. And you see, it's my favorite example because I'm always kind of taking it out. So if I consider f of z, which is equal to z squared, and I search for a fixed point, so a fixed point, z0 is fixed, f, well, this is a definition, f of z0 is equal to z0, okay? That's what a fixed point is. And so what happens for this map? So if you solve z squared equal to z on c hat, what do you have? Well, so I can rewrite this like z times z minus 1 equals 0, if I'm not mistaken. Yes? And then, so this is going to be true, since we're on the complex plane where we don't have divisors of 0, z is going to be equal to either 0 or z is going to be equal to 1. But then what happens? Well, we have a polynomial and we're working on the Riemann sphere, so we have to see what happens to infinity. Well, f of infinity is going to be equal to infinity as well, okay? And so in here we have 3 fixed points, 0, 1, and infinity. And what did we see yesterday? We had that 0 was a fixed point where everything was attracted to the origin. Infinity was somewhere over there where everything was going outside the closed unit disk. And what happens to 1? Well, in 1 is not in the Fatou set. 1 is on the Julia set. So 1 has a special feature. So how do we see, how can we encode this special feature by something which is written in my maps? So, well, what did I do for now? For the moment, I was just looking at the map itself. So maybe now I can look at the derivative of this map and see what happens. If I look at the derivative of my map at the fixed point, what do I get? Well, the derivative of z squared is 2z. So f prime of z is 2z. And so what happens when I compute it at the fixed points? At prime f0 is going to be equal to 0. Right? So now, how do you compute the derivative at infinity? Well, for the moment, we didn't play much with this. But actually, what we can do, instead of, infinity is here, right? Somewhere on the Riemann sphere. We chose these coordinates where in here we had z squared. But nothing tells us that we have to keep infinity over there. So we can put it at 0. And so if I make an inversion, if I consider the map w equal 1 over z, then I can compute the derivative. And so the derivative will be, so the derivative at infinity is going to be again, no, 0. It's going to be 0 because the derivative cannot take any infinite value. Okay, so I will explain to you a little later how to do it, and this will be part of the exercise. Compute the derivative at infinity. Okay, and what happens at 1? Well, 1 is not just it's just an easy point. So we had the derivative is 2z, and so what happens at 1? It's 2, right? So, and actually, what do we see at 1? Let's see. Well, if I pick a point on this side, these points are going to go towards 0. If I pick a point on this other side, these points are all going to be going towards infinity. And whenever I'm here, well, these points are going to go somewhere else. So they are all going away from 1. Well, actually, 1 is what we call a repelling fixed point. I mean, all the points nearby him leaves him for forever. Okay? And so this gives the idea of giving a definition. So we're going to give a definition of periodic point. Well, a periodic point is simply a fixed point for one of the iterates. And then, of course, a point can be pre-periodic if after a number of iterates it becomes periodic. And then we will attach, I will tell you, okay, this point is going to be super attracting, parabolic, elliptic, and repelling. Okay? And, well, this is for me important because I'm going to use it also when I give you the classification of Fatou components. So we saw yesterday that there is this result, which was conjectured by Fatou at the beginning, and then proved with the help of many other people. But this is why I call it Fatou classification. So he was the one who suggested it. And, well, in there, you remember there were these parabolic basin, attracting basins, and rotation domains. Okay? So we are going to put all this in a big picture by giving all the required definitions. So are there questions so far before I go on? Okay. You can always ask them. You remember that, right? So, oops, all right. So, in here, where are my notes? I like to follow my notes so that I don't lose myself. So, definition, well, you take f, a rational function, but actually this definition you can give it whenever you have also an entire function. The same definition holds, because this is going to be a local definition. So a fixed point p and c hat for f is a point such that f of p is equal to p. All right, that was easy. And, well, so, okay. What I did over there was kind of misleading. So I talked about the derivative, but when you talk about the derivative at the point, actually you should talk about the map on the tangent plane. Okay, that's a tangent, that's a linear map where you can compute the multiplier. Okay, so, well, the derivative of f at p is an endomorphism, oops, of the tangent line t alpha at c hat, that I'm going to, yes, let me stick to my notation, is dpf from tp, I don't know why I put alpha in here, that's a p, because my fixed point is p, to tp of c to tp of c hat. That's the tangent line. And so it is the multiplication by a constant, a number, lambda, which is complex. And so this is why it cannot be infinite. Okay? And once you have this, I'm going to call it that we call the multiplier at the point. of f. And, well, P is called super attracting if, well, the multiplier lambda is 0, attracting if the multiplier as modulus, well, strictly bigger than 0 and less than 1, repelling if the multiplier as modulus strictly bigger than 1. And now we are left with the modulus 1 case. So it's going to be called indifferent or neutral if the modulus of lambda is 1. And this case has two subcases. Well, the parabolic case, when lambda is a root of unity, could be 1, by the way, P and Q co-prime, and yes, and P and Q in Z with Q different from 0. Or it could be elliptic if lambda is, well, a number of modulus 1 which is not a root of unity. That is the exponential 2 pi I theta with theta an irrational number. Okay? And yes, and as a matter of fact, this definition comes from parabolic elliptic. And so in here we have this super attracting, but sometimes these three cases are called hyperbolic. Okay? And so you have hyperbolic, parabolic, and elliptic. All right? So once we have this,
sorry, where does the terminology come from?
well, this comes from the well, the automorphisms of the disk. So in here, yes, an elliptic automorphism of the disk is going to be a rotation. In the parabolic case, you have a fixed point in the boundary. And in the hyperbolic case, you have a fixed point inside, where everything is contracted. So this is where it's just a terminology. It doesn't mean much, actually.
Okay, so there's no connection to any other things that are called like that?
No, not really. I mean, the only connection that you will have is that once you have this terminology in dimension 1, you're going to have the same terminology in higher dimension, but not. It's not related to, for example, parabolic PDEs or stuff like that. No. At least not that I know. All right. So, yes, so again, an exercise. So the exercise is the following. If, so this is point 1, if P is not infinity, then the multiplier, lambda, is equal to f prime at P. So it's really given by the derivative, as we know it. If P is infinity, then what you can do, well, you can look at the asymptotic development at infinity. So, and f of z is equivalent to az as z goes to infinity. Well, I'm putting in the modulus so that it's easier. Then the multiplier lambda is going to be equal to 1 over a. Whereas, and if P is equal to infinity and f of z is equivalent to az to the power k as z goes to infinity, with k at least 2, then the multiplier is 0. All right? And, well, the third thing that you can prove is that if f is a polynomial, of degree d, at least 2, then infinity, is a super attracting fixed point. Meaning that it's always a fixed point, and this is not difficult to prove, because a polynomial of positive degree is going to send infinity into itself. This is something that you can prove. And the derivative is going to be always, the derivative as a map is going to be 0. It's going to behave, so f is going to behave like a to the power z to the power the degree at infinity, which means that the multiplier is going to be 0. And so it's a super attracting fixed point. All right, actually this terminology doesn't come from nothing. So let me, oh yes, I have to give you this definition as well. So yes, what I was saying, the exercise that you can do, it's really easy. Is the multiplier is invariant under analytic conjugacy. And this is simply the chain rule. But I will let you try to search for it. And then if you have questions, I will answer to you, of course. And so, well, once we have the definition of fixed point, you can define a periodic point. So, well, P is periodic for f if there exists, well, actually, let's put it like this. If it is fixed for f iterated k times for some k bigger than 1. So actually, an invariant, a fixed point, is a periodic point of period 1. Actually, you can also say the period. So the smallest such k is called the period of P under F, and then you're going to have a set P f of P until f iterated k minus 1 times of P, and then you stop, because if you iterate k times, you're going to get back to P. This is going to be called the cycle. So this is a cycle for f. So a cycle, because what you're having is that you have P, f of P, then you go to f iterated 2 times of P, and then, well, you iterate sometimes, and then at some point, you get back to P. Okay? So this is why it's a cycle, because it came back to itself. Are we good? And so, well, now, well, this is not a difficult thing, so I'm going to state this as a proposition, and you can try to prove it, because it's not difficult. If you have a cycle, if P f of P until fk minus 1 of P is a cycle for f, then the derivative, then the multiplier, of f iterated k times at each point in the cycle is the same. And this is essentially, again, the chain rule. So you compute the derivatives, and you compute it at the first point, and then you compute it at the second point, and you will see that it's the same number. Of course, you may ask, well, what happens if infinity is somewhere in this picture? That's the tricky part. So the proof is an exercise. But once we have this proposition, then what we can do, we can define, so we have a cycle, we have a periodic point for f of some period. So we define the multiplier for a fixed point. We can define the multiplier at a cycle. So the multiplier at the cycle will be this multiplier of f to the period. Okay? So the multiplier of f at the cycle, p fk minus 1 of p, okay, is the multiplier of f iterated k times at one of the points in the cycle. Which makes life convenient. For example, if infinity is in your cycle, then, but there are other points, like 1 is in the cycle, why would you ever compute the derivative at infinity? You just compute it at 1, and that's easy, right? I mean, if you can do it, why not? All right. And so, yes, and as a matter of fact, if infinity is not in the cycle, then the multiplier is simply, well, you're taking k times, you derive it at p, and what you're getting is the product as j goes from 1 to k at the derivative f prime at each point in the cycle. So fj, yes, I read it like this, but I prefer from 0 to k minus 1 at fj of p. So you take the product of the derivative at each point in the cycle. That's exactly what the chain rule gives you. Okay? And so, well, okay. So I will not have time to enter into this, but we can maybe talk about it in the exercises. So there is a proposition. So we've done, so far what we've did was the following. So we gave definitions for attracting, superattracting, parabolic and elliptic fixed points. We generalized this definition to cycles. I mean, up to an iterate, it's the same. That's what he's telling you this. Okay, a periodic point is fixed by a given iterate of f. And so, well, I can consider this f to the power k, f iterated k times, as a dynamical system, and I can study things there. But now I would like to infer some information from this classification to, well, my original question. For example, if I give you an attracting fixed point, is it going to be in the Fatou set? If I give you a repelling fixed point, where is it going to be? I mean, in principle, one could guess. And well, actually what you would guess is the good thing. So if you take f, a rational map of degree at least 2, and p, a periodic point. So this is the set of periodic points for f. Then you have the following. If p is superattracting or attracting, then p belongs to the Fatou set. And if p is repelling, then P belongs to the Julia set. Okay, so repelling periodic points are never in the Fatou set. Yes, that's what I wrote. And attracting or superattracting fixed periodic points are always in the Fatou set. When it gets to parabolic fixed points, then, well, since my map has degree d, those are going to be in the Julia set. So a parabolic point will be in the Julia set. We will understand why later, because, yes, I have 15 minutes left. Yes, yes, yes. So parabolic points will live in the Julia set, whereas elliptic fixed points, I'm coming. It depends. For those, it depends. You had the questions. Oh, no, sorry. So this proposition is something that you can do, you can try to prove by using, so the fact that if you think about it, being in the Fatou set is a local condition. So all you need to know is that you have convergence in the neighborhood of your fixed point now. No, I mean, up to an iterate, you can consider that it is fixed. And now if your map is attracting, what happens? Well, at the linear level, in a very small neighborhood, what's going to happen, since the linear part is attracting, or, well, actually super attracting, so you start with a z to some power, well, this tiny neighborhood is going to be sent into itself. And therefore, you can continue, and you will have local convergence uniformly towards the fixed point. And the same can be done when you have a repelling fixed point. Actually, you could also say, well, if it is repelling, I consider the inverse locally. Locally, I can do it. And for the inverse, it's going to be attracting. And so if it is attracting for the inverse, it has to leave every neighborhood. And so I cannot have convergence. When it comes to parabolic fixed points, I mean, you have this linear part, which is a rotation, a rational rotation. Take it 1. So you start with z. But the map is not the identity. So you have z plus something. And this something is going to tell you something more about the dynamics. So that part, we will see it tomorrow, where we will finally go to a higher dimension. And, well, for elliptic fixed points, it really depends. I mean, it depends means that it depends on the map. Okay, some of those are in the Julia set, and some of those are in the Fatou set. And there is nothing you can do about it. Okay? And so, well, actually, finally, we come to at least giving the definition of the classification that we saw yesterday in the statement of the theorem. So in here, so let me give you one more proposition. So now we would like to describe the Fatou set. And we have this proposition. You take a rational map of degree at least d if omega is a Fatou component remember, these are connected components of the Fatou set, because we saw that the Fatou set doesn't need to be connected. Then f of omega is a Fatou component as well. And moreover, f from omega to, well, its image is a proper map. Where proper means that for every compact set contained in f of omega, the preimage of this compact set is also compact in omega. Okay, so this is the definition of a proper map in case you didn't have it in your minds. And so, well, now what's going to happen is that, well, I shouldn't have erased stuff, but so remember in here we had this classifications of fixed points, super attracting, attracting, parabolic, elliptic, repelling, and so on and so forth, where we're going to take this definition and see what happens for Fatou components. Of course, a repelling fixed point doesn't give you anything in the Fatou set, as it's written here, so you will not have repelling Fatou components. But, well, these guys are going to give you Fatou components. Parabolic fixed points are going to give you Fatou components, and elliptic fixed points, some of them are going to give you Fatou components. And some others, well, there are other Fatou components who cannot happen for a polynomial, but can happen, for example, for irrational maps, who have no fixed points inside. And so, well, in here, I'm going to stick to give these definitions for an invariant Fatou component, but now you know the trick. I mean, if you have a periodic Fatou component, well, the definition is going to be exactly the same as a periodic fixed point. I mean, it's a Fatou component which comes back to itself after a finite number of steps. And the number of steps could be 1. Okay? And if you know the definition of an attracting Fatou component, which an attracting invariant Fatou component, an attracting periodic Fatou component will simply be a Fatou component which is in a cycle where when you consider it as an invariant Fatou component for f iterated k times, it's going to be attracting. And the same for the others. All right? Because it's going to save me, I don't know, 10 minutes of writing stuff. So definition, an invariant Fatou component is, okay, well, first, super, actually usually we forget about the super, so attracting. So it's going to be attracting if there exists a fixed point, a super attracting or attracting fixed point in omega. And yes, and the sequence of iterates converges locally uniformly to this fixed point. Oh, I didn't put the name. So the fixed point is called P as usual on every compact subset of omega. So actually what we are saying in here is that, well, in this proposition, what you can prove is that locally you have a neighborhood, a small neighborhood, where all points converge to the fixed point, which is attracting or super attracting. And what we are saying is that we can look at the biggest open set where this happens, take all these pre-images. Well, this is going to be a Fatou component. Okay? That's what this is saying. But you could have a parabolic domain oh yeah, and by the way, so in here, since we have the uniformization theorem, and our map is as a map at a degree bigger than 2, so it cannot be a whole, how to say it, just one Fatou component. That's what I want to say. In here you have that this is going to be simply connected, because all these points are going to converge to this fixed point as orbits. And so it is, by Riemann's theorem, it's going to be holomorphic to the disk. And so it's really, when I do this picture, which is supposed to be a disk, and I put everything going to 0, it's really the model that I have in here, right? The model is going to be a disk with 0 as a fixed point in the middle. And and inside this, you will be able to conjugate your map to, if you have a super attracting fixed point, it's going to be z to the power d. And if your fixed point is attracting but not super attracting, you're going to be linear. inside here. So life is going to be super easy once you are in the Fatou component. Of course, you have to be in the Fatou components. So a parabolic domain, what it is, well, if there is a fixed point, a parabolic fixed point, well, actually, a fixed point, let me write it like this, because we can be more precise. P, but this time, the fixed point belongs to the boundary of omega. And moreover, the multiplier lambda of f at the fixed point is 1. And this is something that's going to happen because we're talking about Fatou components. This is not usually the case if you consider a local function, just a function which starts as like the, well, a linear part. It could be that this linear part is a rational rotation. That could happen. But if you start with a rational map of degree d and you consider it as a global thing and you study Fatou components, well, whenever you have a parabolic domain, the derivative is going to be 1. All right? And the sequence, and of course, again, f iterated k times, so the sequence, all the sequence, not taking up subsequences, converges to p locally uniformly on compact subsets of omega. All right? And so we are left with what one usually calls a rotation domain. So I'm going to be very precise today. So it could be a Siegel disk. If omega is simply connected. And well, what's going to happen is that there exists a biholomorphism, so H from omega to the disk. This is why it's called a disk. A biholomorphism. A biholomorphism is what I called also an analytic isomorphism, such that, well, H composed with F composed with H inverse. Remember this conjugacy, so it's going to conjugate F to a linear map, actually to its linear part. So e to the 2 pi I theta z with theta, which is going to be, irrational. All right? So, and actually, what you could say is that I have a rotation domain, so there is a subsequence of iterates where I converge to the identity. That's something that it is going to happen for Siegel disk or for Emerald rings, but I prefer to give you the precise definition. So even if you're in a Siegel disk, it's really going to be biholomorphic to the disk where you have an irrational rotation. So what's going to go for orbits? Every orbit is going to accumulate on a circle, on concerted circles. And you see that you pass continuously from one circle to another. And the last case could be a Hermann ring. Well, in this case, omega is doubly connected. Meaning you're going to have an annulus, and this is what's going to come after. And there exist, well, two radii. So I'm going to, well, actually one radio, as are bigger than 0 and less than 1. And a biholomorphism, H from omega to this annulus, which is simply the complex number such that, well, they're in modulus bigger than r and less than 1. So you can always normalize one of the two radii to be 1. that's, well, that's an easy trick. A biholomorphism. Yes, such that, again, well, H composed with F composed with H inverse of Z is going to be, again, this irrational rotation that we saw with the irrational. So, but this time, you're not having a fixed point. Okay, it could be punctured. Could be that R is, sorry, it could not be punctured. Because if it was punctured, that it would create problems. And yes, of course, each possibility is exclusive. So if you are in a Fatou component, which is a parabolic domain, it cannot be also a Hermann ring. All right? This is simply connected. This is doubly connected. If you are in these cases, well, if you are a Siegel disk, you're simply connected. You cannot be an Hermann ring. And actually, as a matter of fact, polynomials cannot have, yes, I'm going to finish, Hermann rings. All right? Yes?
The word before connected, if omega, Hermann
Doubly. Is doubly connected. Doubly connected because you have a hole.
Yeah.
It could be multiply connected. So this is related to the P1, the fundamental group that of your set. So it could be, in principle, it could be multiply connected. So you could have several holes. But as a matter of fact, whenever you arrive to here, for a rational map of degree D on the Riemann sphere, the only thing, the worst case that can happen is a hole, one hole, a doubly connected. So yes. I think my time is over. Yeah. So I'm going to, well, stop here, just waving my hands a little, without writing it at the board because I wrote it yesterday. So now what we know is that Fatou's classification, what it tells you is that if you have an invariant Fatou component, it has to be one of those. It cannot be anything else when it is invariant. All right? And so just a little history, because one has to give to Caesar what it's Caesar's. So super attracting fixed points actually have been studied by Butcher, and then you have Koenigs. But essentially this classification, so the fact that you can have an attracting invariant Fatou component, this goes back to Fatou. Parabolic domains were discovered by Fatou and Lowe as well. But you see in here you have two different names. So a Siegel disk, well, this were discovered, they were first constructed by Siegel. And this is kind of like, this is the beginning of the century, of the 20th century. This is like 1945, if I'm not mistaken. And Hermann rings arrived later. And they arrived later because you cannot find them, they don't exist. You can prove that they don't exist for polynomials. Okay, and so to construct them, you really need to have a rational function, something which is actually, if I'm not mistaken, they are constructed by using Blaschke products. And as I was saying, essentially this is it because, as we saw, well, in 1985, Sullivan proved, I mean, we didn't see the proof, but we saw the statement, that there are no wandering Fatou components. So up to an iterate, so if you take a Fatou component, up to an iterate, it's going to be an invariant Fatou component for your iterate, your given iterate. And then it has to fall in one of these four categories, and that's it. And with this, I beg your pardon, I stole you 3 minutes, and I thank you very much for your attention today. Yes?